Good afternoon, everybody. Please take your seats. Welcome to Technical Session 3. My name is Dave Phelan from APNIC. This afternoon, we have three speakers. We will have Aris Rizdianto from the University of Singapore, as well as an ambassador for the Open Networking Foundation. Following him will be Jeff Houston, the Chief Scientist of APNIC. And to close us out, we'll have Fabricio Mazzola from UFRGS. If I could ask that all speakers please keep to their 15-minute time slots, as this room is running back-to-back this afternoon. So first up, I'd like to invite Aris to the stage. He'll be talking to us about the design, development, and operation of an Sdn-based BGP playground for networkers. Thanks. Green button.
Okay, hello everyone. My name is Aris from National University of Singapore. I also represent ONF, Open Networking Foundation, as one of their ambassadors. Today's presentation is about one project that's supported by APNIC Foundations, which is try to build and operate Sdn and Bgp testbed over Asia countries. Okay, this is the agenda of presentation today. We start with some experience, and then we will conclude with some detailed use case verifications. Okay, before we going to some details of the project, I would like to share some of our experience in deploy and operations of testbed or playground. Okay, our team members basically already have been working together since a couple of years, since 2012. Okay, mostly is supported by the Asia Connect project, which is from the European Commission. Basically, they want us to build a testbed across Asia countries. Okay, the intentions in that time basically is we found that there is a gap, especially the knowledge gaps between some of the Asia countries, usually from Japan, Korea, or Taiwan, with some other Asia countries, especially in the Southeast Asia. Okay, even like me in Indonesia. So we decide to build the testbed that can be shared amongst all the communities in the Asian countries. Okay, so in general, we deploy many different topology, like not only the networking, but also cloud and some of the data-centric testbed. But in terms of the network itself, sorry. Oh, sorry. Yeah. In terms of the networking itself, next. Okay. In terms of the networking, we have several trials. So basically, the first place we just try with the overlay SDN VXLAN tunnel. Okay, and then since the number of sites is increasing, so we move to some hybrid connections using the VXLAN tunnel and also the BGP connections, and of course, both of the network can be interconnected. And then we found that we may need to reconstruct the topology. So we decide for some of the, you can say like the stable sites, which is the main sites, we use as a core site, which is we configure it as a fabric. Okay, and then there will be a small site that can connected to one of the sites. Okay, so we found that it's very useful for the academic, and then we think of whether it can be also useful for professionals, what they say, experience. Okay, So the idea is we want to use this testbed for not only for academia, but also for the professional to play around with the, you can say like the futures networking of the internet, and then we can deploy many different solutions. Okay, so we craft a proposal to APNIC, and then with this all the objective, as we can see here, the main objective will be building the prototype of the testbed, and then the most important, the players or the participant can be or can bring their own equipment. You can say like virtualized equipment to connect to the testbed, and then we provide training, like online training, and then we also ask somebody or ask many people that want to share their knowledge to join our project. Okay, so the design is very straightforward, as we mentioned before. So we have several sites which is stable. They have very high-speed network. So we make it as you can say like the core sites. We configure it as the fabric, or we usually they configure in the IXP. Okay, and then some of the remote site will be connected whether to simple VXLAN tunnel, or they can just use the BGP overlay connections. Okay, so and then in terms of the implementations, since we want to connect the testbed with the real internet, so we got support from the APNIC to get our own IS number, and then we have the IP4 and IPv6 prefixes that assigned to our testbed, and then we deploy some of the devices in some of the sites that we define. Like now we have in Malaysia, Taiwan, and also in US for the upstream to the internet. Okay, and then for the detailed implementations, we use many different hardware and softwares depending on the requirements, because some of the upstream may not allow us to connect using like software routers. So we don't have any other choice. So we need to use hardware routers. But in some of the area or some of the peering with the research network, right, we can also peer with the software routers. Okay, and then we also deploy some SDN controller in the network. And then since we connect to the internet, we must follow the rules of the the internet operations. So we also sign agreements with the vendors because the threat can be come to our testbed as well as the threat can be generated from our testbed. Okay, let's discuss more on the use case, because I think it's more useful what we can do with this kind of playground or testbed. Okay, basically, since we got the project on the knowledge part of the grant, so we provide 4 different stages of training for Sdn and Bgp. So we deliver the basic SDN, including the Linux, because now every configurations in the SDN or even in the cloud or whatever it is will be based on Linux. And then we also deliver training for the advanced SDNs, which is basically it's try to adopt the P4 programming in the hardwares. And then the third one will be introducing the routing and also BGP. And then the last one will be more complicated one, how we can use the SDN and BGP together for different use cases like the SDX or even RPKI deployment or enforcement. Okay, and then the other use case with other project basically try to deploy some service-oriented observations, because we know that we are only the testbed, only the testing environment. So we need to have, you can say like emulate traffic inside the testbed itself. So we find a way how we generate different type of emulated services, and then how it will connected. And then of course we may need to deploy some observations mechanisms, including deploying observer agents like honeypot and others methods to deploy agent to do the observations. Okay, so let's try to go detail on the basic SDN training use cases. Okay, so basically we have this training syllabus. Okay, so as we mentioned before, we not only introduce the networking part, but we also introduce the Linux. Okay, and then we introduce the SDN, means that SDN it's coming from the Stanford University, and then now it's become one of the ONF what they say main driven knowledge. And then of course we start with the open row SDN, which is the original idea of the SDN and some of the SDN controller that available till today. And then for the lab sessions, we use the ONOS SDN controller because ONOS is one of the SDN controller that now is robust enough to be deployed in the productions. And then the last but not least, basically we try to help them to help the participant to deploy some basic SDN applications that we can customize depending on the requirement. So if you're interested with the ONOS project or ONOS SDN controller, you may check with this link. Okay, so the unique of this training, basically we have like multiple level hands-on training. Okay, because the first level actually we use training from the APNIC Academy. It was very nice. It all web-based, everything guided, right? But and then it's not really get our hand dirty, right? So and then we give them pre-configured VMs, okay, that already installed by all the SDN components. And then they can play around with the VMs, and we guide them how to configure the basic configurations. And then the last one, we show them how the SDN can be deployed in worldwide like network. So we in here actually we deploy in 3 different locations, 1 in Taiwan and 2 in Malaysia. And then we ask them to play around how to check the flow, how to allow the communication between one host in this side and the other host in other sides. Yeah. Okay, so this is the result of the participation and feedbacks. So basically, overall is, you can say like good enough. But the most important here actually the level of diversity, right? So we can see here, because one of the parameters of the APNIC run, we need to have some diversity. So here we have more than 30% of the female participants, which is we got some help from the Myanmar, because many of the Myanmar students actually is female, despite of something happened in their countries. But yeah, thank you for the help, and we really appreciate it. Okay, so and then what can be improved is very straightforward. Somebody say that 5 days is not enough, but somebody say that and we need more complex applications. It is okay. And then of course we need to have online training instead of we need offline training instead of the online training. Okay, so okay, so yeah, let's just jump to the last use case. Basically, try to develop services in the the testbed. So basically, we want to emulate the large-scale BGP network in our testbed. Okay, and then we want to do many different experimentations, and of course, we cannot deploy in the physical infrastructure. So we decide to deploy using containerized BGP router with Quagga or FRR. And then for the deployment, to speed up the deployment, we use the Kubernetes with the worker nodes. Okay, so this is the example of the deployment that we did. So in here we can see multiple Kubernetes pods running Quagga router. Okay, and then depending on topology that you want, you can customize it because you just changing the peering configurations, and then one or two routers inside the cluster will connect to the either reset network or internet to get the real route from the internet. Yeah, and then this is some testing and verifications, and then this one is more how we need to move forward. So we want to do many different experimentations, including the IPv6, RPKI deployment validation and enforcement, and then the XDX, as we mentioned before. And then we want to do some BGP route hijacking simulations. Okay, thank you. If you have any questions, I will be very happy to take it.
Thank you, Aris. Any questions, please step up to the mic, state your name and your affiliation.
Hi, wonderful presentation. And this is a very good resource for research purpose. And I myself I'm Vidya Sagar. I'm from CERT India. I'm a cybersecurity researcher. So I think I might have missed it. Whether there is any publicly accessible instance for this lab?
Oh, you mean this lab is publicly accessible?
Yes, that's very much important, right?
Yeah, currently we just open for the our community. Okay. But of course, if you want to join our community, we are open.
Okay.
Okay, just contact us in the email, and then we will try to get you on board in our community.
Okay. Yeah. Just in case if that is not possible, and do we get any documentation so that we want to deploy it in our own premises, in our own hardware? Whether that is possible, whether it is documented anywhere? Yeah,
most of the documentation you can see in the website. Okay. But some technical details like how we peer with the upstream, we may not be able to share. But most of the software, hardware, the software, everything we can share easily.
Yeah. All are Bird and Quagga, all are open source.
Yes,
anyway.
yes.
But
yes.
I had gone through the website and I couldn't find any documentation. That's why I came here.
Yeah. We will try. We have some GitHub that not published yet.
Okay.
But later on, if we only publish, and including all the training materials, everything that you can repeat in your environment.
So right now, don't have any presence in the GitHub for the documentation. Okay, thank you.
Okay.
Hi, my name is Dhruv. One quick question: like, if we go to ONUS website and they have Mininet and they have their own set of use cases where they share how to do the demo. So how's your playground different from what's already there? So could you give some highlights? Like, what's the unique thing that you did?
Okay. Mininet actually is not really deployment, right? Mininet is only for the testing. It means that you want to play with some little bit small functionality, you can test with Mininet. But if you want to deploy, so you need to craft your own infrastructures. For example, Mininet is based on the Open vSwitch, right? The software switch. So if you want to deploy in many different locations, so you need to install the software switch by your own, okay? And then you may configure all the ports, everything by your own. You cannot rely on Mininet to create all these switch configurations all over the locations, okay? But of course, there are many different automations that you can use, but Mininet usually is only single host, okay? It's not be able to be deployed in many different locations, yeah. Is this answer your questions? Yeah.
Yeah, hi. So I'm Azhar and I'm one of the APNIC community trainer. I really like that. I just have one quick question. I think I missed that part. You were talking about the Sdn controllers and you mentioned that you some sort of more happy with the ONOS and have you done any comparison between the controller? Why do you think is the one is better for your, training environment in the other one? Is there a reason behind it? I want to know.
Okay, I think it's a little bit subjective. Okay, why I choose ONOS because I one of the ONF ambassador, right? So in terms of the technical aspect, I know better ONOS than the others, and of course, I have some channel that I can always ask directly to the developer. I mean, like what kind of problem that can be happen and then how to solve it. Yeah, of course it can be. I mean, of course we can use many different controllers. Like for example, we also done with the Open Daylight using the APNIC website. But yeah, it will be applicable for all the controllers. Yeah.
One more question. Any other questions? We can feed them back to Aris after the session. Thanks.
Okay, Richard Ma from National University of Singapore. Okay, so I see that you mentioned that currently there are 3 physical sites, right, in Taiwan, US. Is there any physical kind of setup in Singapore?
This is a good questions. Actually, the issue why I cannot deploy in the NUS because the NUS, I mean the part connected to the research network actually is not in my department. It's in other department. So it's not easy to put the what they say some infrastructure in that other department. Yeah.
So maybe we can talk.
Okay, later on we can discuss. Yeah, of course.
All right. Thanks you very much, Aris. Give Aris a round of applause. All right. Next up, joining us remotely is APNIC's Chief Scientist, Jeff Houston, who will be talking about the path to resolveless DNS. Are you?
Hi, yeah, thanks. Hi, good afternoon. Time is short, and I think I've got just 15 minutes. Is that right, Dave?
15 minutes plus Q&A.
Yeah. Okay, so routing and transit's all very interesting, but it's so dated. It's so yesterday, because quite frankly, the last 10 years has seen an internet that delivers content from content data networks, and the only transit across the internet is now the last access mile. Routing doesn't matter. We've made it irrelevant. So what matters? What's actually important? And interestingly, what's important is actually the namespace. What's important is actually the DNS, because that's the bit that we're relying on to keep the glue of the internet together. Routing doesn't matter, the DNS does. And so this is actually a talk that looks at the way we're changing the DNS to make it faster, more secure, and actually better encrypted along the way, because that's the bit that's important in today's internet. Now, the way the DNS used to work is the sort of classic example of, you're an application, you've got a little stub resolver on your host, you speak to some large caching system, a recursive resolver, that goes and finds the right authoritative server to ask the question. The whole magic is in the cache, because without caching, the DNS would run like a dog. Caching is everything, and the recursive resolver is very important. But not everyone runs a recursive resolver on their own mobile device, on their own hardware, because, the cache would be tiny. Where you get the most leverage is in large caches. And it was pretty common for the ISP to run that recursive resolver on behalf of the clients. And then all the clients behind there would go, well, I'm just configured with DNS. My ISP looks after that. Life is wonderful. But it's not wonderful. The DNS can be astonishingly slow. And these interactions with resolver caches doesn't make it faster all the time. It just makes it less predictable. Oddly enough, the DNS is being used by many countries and regimes as a convenient point for content managing and filtering. There's a court case where COD9 got caught up with in Europe for resolving names that led to some alleged IPR theft. And the DNS is always that critical point where folk go, if you can't resolve the name, you can't get to the site. And so it's at the pointy end of a fight for control. And if I saw your DNS feed, you have no secrets anymore. Everything you do is in the DNS, and everyone knows it. And so DNS is a rich source of metadata. And interestingly, also ISPs have figured out that if you're going to somewhere whose name doesn't exist, what a convenient excuse to actually advertise themselves. And here's an example. It's a few years back where a large ISP in Australia decided that instead of delivering you the fact that that name doesn't exist, it will redirect your browser to a site run by itself that does its own search. Unfortunately, this was very common at the time, and it still exists across the internet today. And so this stealing of search by the DNS actually prompted the Google giant to respond, and it did. And it opened up its own open resolver service with one promise. It never, ever, ever lied. If it was no such domain, it really is no such domain. And it gathered a lot of momentum very, very quickly. But in gathering that momentum, it fundamentally changed the DNS architecture, because now between the end client and this open recursive resolver, and there's more than Google out there, of course, there's now an internet hop. There's a hop across the open internet. Now, how many folk are using this? Well, there's some measurements we're doing continuously, and up to a quarter of the world have their DNS queries passed into Google's DNS service. Only 70% actually use the local ISP, and another 19%, yes, that adds up to more than 100, I know that, actually use other DNS servers, normally in their own country. 1/4 of the world are having their queries passed across the open internet to an open resolver. That's a problem. The DNS protocol itself is not encrypted. Anyone can see it if they care to look. Anyone can corrupt things if they care to try. This is not a secure protocol. And that large transit hop to get to a Google server has astonishing potential for third-party monitoring, interception, substitution, and all kinds of bad behaviors. And these days, folk like Akamai, for example, use the DNS to figure out where you are. If you're leaping across the internet to go to Google, exactly where are you? The DNS is not helping a lot here. But the major issue was that this was a gigantic privacy issue. 1/4 of the world's users are having their DNS queries, that clear window on what you're doing, actually being an open access window. Anyone who cared to look could find stuff, a lot of stuff about individual users. The response, coupled with the Snowden papers, was to clean up our act a lot. And there were a number of protocols that got developed that basically passed the DNS resolution protocol across encrypted channels. TLS, QUIC, and HTTPS are all variants on the same theme, where you actually wrap up that DNS protocol inside an encrypted channel. It has a number of really good properties. If I try and mimic 8.8.8.8, as a Turkish ISP tried, with DOT or DOQ or DOH, you can't do that, because as a stub resolver, I'm authenticating the identity of the recursive resolver at the other end of the session. So deliberate session interception just doesn't work no more. It encrypts. If you're using DNS over HTTPS or DNS over QUIC, then there's no head of line blocking. And all of these are stream protocols, no fragmentation issues. It works. It's brilliant. But let's look at one in particular, DNS over HTTPS, because this is a fascinating sort of opportunity. One view, espoused by Paul Vixie, was there's no technology here. It's just a political answer. If you really want privacy, use a VPN. DNS over HTTPS is fluff, to paraphrase what he said. But I don't think so. I don't think it's fluff. I think, firstly, it's hiding in the crowd, because all of a sudden you're using the same port as everyone else, TCP port 443 or UDP port 443. Much harder to isolate that DNS traffic and treat it differently. You've actually got generic HTTP caching controls as well as recursive resolver controls. You've got reordering, parallelism, prioritization, and header compression. HTTP is a remarkably good protocol these days. And all of a sudden, I don't need to use my local platform resolver. If I'm an application running in one of these mobile thingies, I don't have to worry about Apple snooping on the behavior of my app, because my app can bypass all of that and go directly to a resolver that my app chooses to use. all of a sudden I'm not leaking information even to my own local platform. And interestingly, these days, DOH is actually the dominant form of encryption for DNS queries. Seriously. We're doing a collaborative research arrangement with Cloudflare, and this is some data coming from Cloudflare's 1.1.1.1 service, where we're actually looking at the protocol being used to query that service. Now, 75% are over normal old UDP, true. But the next biggest, 18%, is actually DNS over HTTPS, and just under 5% for DNS over TLS. So DOH is actually the dominant form of encryption. But what's really fascinating about DOH is the ability to push, the ability to say, you're going to ask for this, let me give it to you straight away. Now, this was great for style sheets and other HTTP objects, but if the DNS is just an HTTP object, you can push answers directly from the server to the client, directly. No recursive resolvers, nothing. And HTTP 3, yeah, it's there too. HTTP server 3, server push is in there. So I can send you DNS answers as a web server. Why would I do that? Well, you don't have to resolve the names. I can look at all the names in a web page I just delivered to you and send you all the DNS resolution answers even before you ask. I'm pre-provisioning. And that's a hell of a lot faster than asking the DNS. And so the other thing is, you aren't querying the DNS. You are not leaving footprints anywhere. You are not generating metadata. It has some astonishingly good privacy benefits because your behavior is now muted. No one actually knows where you go or whether you follow these unrequited DNS responses or not. That's your business. The DNS won't rat on you and tell others what you're doing. For example, look at this search page result from Google. When I query something, I get a whole bunch of URLs out there, yes? What if they all had the DNS results pushed with them? So which one I go to is only known to me and not even my DNS system. I'm telling nobody. Now, there's a real problem with this, as good as it sounds, is how do you recognize truth and tell the difference between truth and a lie? Now, the issue is secure transport is great, but it's no substitute for actually understanding the authenticity of the DNS. If I really want to assume, ensure that those answers are correct, I need to use DNSSEC validation, which means I need to validate those answers. And all of a sudden, life is incredibly slow. Or is it? Because if I can push you the DNS answer, why don't I push you the DNSSEC validation answers too? I know what you're going to ask. I might as well just tell you what the answers are. And indeed, I could package the whole lot by using chain responses. So now the response is in a single DNS object sent across a streaming protocol, so size doesn't matter. And you, the client, can directly authenticate that answer. All of a sudden, you know the answer's authentic, it's current, it's complete. No one's lying here, because you can't lie. So it doesn't matter that the server's giving it to you or anyone else. DNSSEC is telling you that's the real deal. That's the DNS data, no lies, no mucking around, no interference. Now, this works for signed names. What if names are unsigned? Don't trust the thing. If it's not signed, don't do this, because unsigned DNS data is just dangerous. You really don't know what's going on here. So if the stuff is not signed, don't bother pushing. That's easy. So if it's signed and if you push it rather than using resolvers, all of a sudden there's a huge amount of control placed where we are placing control in the internet. The internet's not a transit experience anymore. It's an application experience. It's experience up at the upper layers of the protocol stack. And this directly gives control of name resolution into the upper layers themselves. The server pre-provisions the client. The client can do DNSSEC validation and doesn't rely on anyone else. It can replace all of those stupid UDP timers and the entire rigmarole and complexity of the DNS resolution protocol. It's over a secured connection with an authenticated server. As long as the data is DNSSEC signed, this sounds brilliant. And as I said, if it's not signed, not going to work. Why? Well, I actually think there's a fundamental change going on here, and it is all about the changing economics of the internet. The revenue base isn't in routing and transit. Carrying packets is a featureless, bleak world of declining value. No one cares anymore. What matters now is actually this application and content. So the incentive and the money lies in making it faster and better. Infrastructure is just being squeezed. Applications are actually picking up on that and doing more of the work themselves. And innovation in the DNS is extremely challenging. So applications are just bypassing the entire DNS infrastructure and using resolvables to actually get through this. So is there a role there for resolvables DNS? I think there is. But the whole issue is now DNSSEC signing is actually, if you will, the problem. Only a few zones are signed. I think it's about 5% at most at the moment, which is a pretty small number. Most folk don't sign their names because DNS over UDP and signed responses don't go well together. It's slow, it's unwieldy, it's not very robust. And pre-signing for large zones doesn't work. Signing on the fly is fragile. So very few folk validate. But what if we move to a world where DNS over HTTPS, as we're seeing with Cloudflare, becomes the dominant way of doing things? That all of a sudden we can contemplate chained responses and chaining. If the zone is unsigned, sucks to be you. But if the zone is signed, this stuff becomes lightning fast. And that's important because we've been spending most of the last 5 years of the internet trying to eliminate those huge time penalties, those huge privacy leaks, those huge failure points that constantly bedevil the internet. The whole thing about CDNs was to compress the internet to make it faster, cheaper, and better. And oddly enough, Resolvable DNS can actually do a huge amount down that direction. It passes control back to the application and cuts out the infrastructure, which is basically tired, ailing, and underfunded. It allows the end client to directly validate. It is a massive lot faster, and it actually rewrites the entire privacy picture so that it hides the client from everyone. And for that reason, it's a fascinating evolution for not just the DNS, but for the internet itself. Because if we're spending all of this effort over the last decade to actually replace transit with CDNs, to actually ignore routing because it just doesn't matter anymore, trying to rewrite the non-blocking protocols into things like QUIC and tuning our end-to-end transport to make it faster. All of this work and innovation is happening at the application level, not at the infrastructure level. And so it's only natural that the DNS, as we knew it, is going to get sucked into it and is going to change fundamentally. When's it going to happen? Well, I think it's happening now. It's just a case of looking and understanding for it and finding those places where the browser is now taking over the job of the infrastructure. So resolvables DNS, a DNS where the server pre-provisions, it's logical, it's immediate, it's happening. Thank you. Questions?
Any questions for Jeff? Please step up to the mic and ask your question for Jeff.
So Tobias Fiedek, Max Planck Institute for Informatics. So we have routing basically removed because it moved to the CDNs, and you say DNS is walking the same path now. So what of the internet is left then, which is not part of the CDNs?
Users pay for the internet, no one else. And users pull about 90% of their content from CDNs. It's all streaming. And so, quite frankly, everything else is marginal. And as we saw with voice over IP, if you spend 50% of your money to actually engineer a response for less than 1% of your traffic and 0.001% of your revenue, you're going to die. No one's in love with the internet. We're in love with consumers paying us money. And if you don't adapt, you die too. So no, it doesn't matter anymore, because when we wanted a bigger, faster, better internet, what we actually found was there's an abundance of storage, an abundance of compute, an abundance of comms. We can afford to pre-provision. We can afford to put 1,000, 10,000 copies of the same silly video on every Netflix cache on the planet. We can afford to do that over Netflix's own provisioning network and then just deliver it down the last mile then and there. So that's what's happened over the last 10 years. The internet is not changing, it has changed. It seems silly to be wed to a DNS from 20 years ago when the rest of the internet's gone, nah, don't need it anymore. And we don't. It's quite a fascinating change. And thank you for your question.
I have a question from online, from Adash. Which is faster, HTTP over DNS or HTTPS over DNS?
Anything over the DNS is a disaster. Don't use the DNS as a tunneling protocol. That's just crazy. But if you're saying which is faster, DNS over HTTP or DNS over HTTPS, well, the answer is you wouldn't bother with DNS over HTTP. I might, quite frankly, you know, it's an open protocol. It's a joke. DNS is over HTTPS. And what we're really talking about here is whether it's HTTPS 2, which is TLS, or 3, which is quick. Which is faster? Quick. Hands down, it's quick.
And one last question from the room.
Hi, Jeff. Sanjeev
Hi.
here, IPv6 forum and all. So now I'm just wondering if we are all going to be just using Firefox to connect, and you're just telling us that all the last 35 years of the fights over whether the internet is a 4-layer or 7-layer are all meaningless. Firstly, this is the wrong forum. You can't like walk in here into a group of network engineers and say, nah, you're all dinosaurs. And secondly, what does it do to our plans or APNIC's plans or the Internet Society plans for all the other engineering? I mean, you just told us we're all useless. I mean, in a much politer way.
Okay, so 80% of the world's users use...
Do I need to look for a new job?
Yes, 80% of the world's users use Chrome, not Firefox, Chrome. Chrome is the dominant browser by 3 orders of magnitude over everything else. What Chrome does is the internet. Now, that's just basic reality. So the next thing is, this is not a command economy. We deregulated 30 years ago. The market always wins. What consumers want to pay for is what we build. If they don't want to pay for it, you are wasting your time, and so am I. Because this is a market. I can't order users to do anything, and neither can you. You've got to build infrastructure cost effectively to match what they want to do. And what they want is cheap streaming content over massive broadband access systems. That's what we're building. Routing doesn't matter. Transit doesn't matter. Google has found it more effective to build its own private intercontinental infrastructure because it's cheaper and more effective. It's a market. They can do what they want with their money. If it works, they make more money. If it doesn't, they go broke. No one's forcing anything here other than you and I as consumers. So the issue is, if you follow the consumer and what they want and how they want it, consumers really do want bigger, faster, better. And CDNs is the way we've found it to actually do that. So if I'm saying, yes, this is reality, and smacking you around the head with reality, I don't apologize for that. This is reality. If you want to argue with reality, fine. I have a few quibbles about gravity I don't like either, to tell you the truth. And aging is kind of a bugger. But, you know, that's reality too. You just got to live with it.
No, Jeff, I'm agreeing with you. I'm just saying these are things we don't say out loud, please.
I've just said it. Sorry, I'm being very uncouth, and it had to be said. Thank you.
Thank you very much, Jeff. Thank you. Everyone, give Jeff a round of applause. Last speaker for this session is Fabrizio Mazzola, and Fabrizio will be talking about Lost it. Fabricio will be talking about the latency impact of remote peering. Fabricio, are you with us?
Oh, yes. Hello.
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 Yep, we can hear you. Your
Yeah.
slides up on the big screen.
Yeah. Yeah. Can I go?
Just 1 second.
Okay. Sorry.
Almost there. All right, I think we're okay now. Yep, you should be okay now, Fabrizio. All good.
Hide. Oh, yeah. Yeah. Okay. So thank you for the introduction. So I'm a PhD student at UFRGS in Brazil, and I'm a visiting, sorry, I'm a research visitor at the University of Waikato in New Zealand, and I'll be presenting our work on the latest impacts of remote peering. That's an ongoing work that we are doing with folks from FURG in Brazil, Queen Mary University on London, and also University of Waikato here in New Zealand. So as a bit of context about work, so the task of how to deliver traffic is an increasingly complex aspect of the internet today. This happens mainly considering that many modern applications generate large volumes of traffic and have strict service requirements such as low latency and good quality of service. And as a consequence, autonomous systems are constantly increasing their interconnection capacities and expanding their footprint to improve their network performance to its customers and to be as close as to the customer is possible. And IXPs in this context are key elements of this process, so as they can help shorten internet paths, reduce interconnection costs. Currently, there are more than 800 IXPs deployed in the world, with the largest one surpassing 1,000 members. And our original motivation of IXPs was to keep local traffic local by connecting geographically close networks. But unfortunately, this is not true anymore. In the last few years, there's been a growth in the usage of remote peering, which is where an AS is not physically present at an IXP facility and reach the IXP via a layer 2 connection, allowing them to widen their peering footprint with a quicker and easier setup, lower installation costs compared to a local peering, and no need for additional hardware. So it probably removes the bureaucracy of having to open a new company abroad or having to pay for colocation fees. And to cope with this demand for peering in the recent years, IXPs and remote peering resellers have expanded their offerings to this service. So, for example, the Links IXPs, as we see in this figure, there are ASs based in 81 different countries connected to them as today. So apart from being very good of having new peering opportunities and a lot of new members so you can peer with, having these remote peerings adds a lot of complexity to traffic engineering choices, since the ASs have no visibility of which peers are remote or not at 1XP, and they don't know pretty well how remote connections could affect their interconnection performance. So despite being widely used in the internet today, there are mixed feelings by the community about remote peering, mainly about the performance of it, which is currently a data poor discussion. Many discussions include the fact that we cannot ignore network links crossing the world to connect at 1XPs, that layer 2 services adds more complexity to the network as they are harder to monitor, that remote peering can lead to routing inefficiencies and the add of insane path, and that it's harder to know the latency impact that it could affect the peering interconnections. So with these different views in mind, the goal of our work is to investigate the latency impacts of remote peering by putting real data to the performance discussions. And in our work, we have three main bases of it. And first, we discuss and analyze the challenges of inferring remote peering at XPs. After that, we want to have an updated view of remote peering deployment, including the number of interfaces, prefixes, and routes being announced via remote connections at different XPs. And lastly, we want to understand the latency impacts of remote peering in the data plan. For example, to reach remotely announced prefixes and when comparing to a local peering alternative, if possible, into the IXP or even a transit provider outside the XP. So in our work, we analyze so far 8 IXPs deploying 5 different countries. So we look at 3 in Brazil, 1 in the UK, 1 in the Netherlands, 3 in the US, and 1 in South Africa. We selected the 6 of them are among the 10 largest IXPs in the world by the number of memberships. And we selected them initially, this subset, because they provided us with both vantage points inside the IXP that enables us to do our measurements and also available routing data that we could use for our prefix classification about which prefixes are being announced via remote connections. So for that, we use mainly BGP routing data from PCH archives and the IXP looking glass servers for some of the IXPs. We also use route views BGP data as a support for some of our claims. And as a tool of measurements, we use Scamper for all of our measurement campaigns. To understand a little bit and to give details about how and from where we do perform our measurements, so we use vantage points located inside route views collectors at the different 8 IXPs, and these vantage points are directly connected to the IXP LAN, as you can see from this figure on the side. We also, from this vantage point, we perform 2 different types of measurement campaigns. So the first one is to measure delay to the IXP interfaces in each of the IXPs. And this campaign is mostly to identify how far or how close a network is from the IXP LAN. As you can see in the green arrows in the figure. The second measurement campaign we did was trace route measurements to remotely announced prefixes in the IXPs. And in this case, we tried to compare using different types of connections, such as remote peering or a local peering if available for that prefixes, or even a transit connection outside the IXP. So we could properly compare the latency to reach these prefixes using different types of connections. As you can see in the orange lines in the figure. Yeah. So an important question that arises also is how do we infer remote peering at the XPs? So during our studies, we found out that inferring remote peering is still a very challenging task. So when using the state-of-the-art methods, we found out that unfortunately it provided insufficient inferences for some XPs, especially the Brazilian ones in our case of analyzed XPs. And it was mainly because there was a lack of AS peering information on public data sources such as PeeringDB for most of Brazilian ASs, because it's not a very they are not very encouraged to announce that from the last 10 years. So only recently they have been doing this movement. But this can affect also in IXPs from other areas that this information is also not available. So as the methodology of the state-of-the-art heavily uses this data for remote peering, it didn't work so well for some cases. So to work around this issue, we investigated remote peering in 2 different perspectives. So a geographical perspective that is using a latency threshold of 10 milliseconds for the RTT to an IXP interfaces. And this methodology was proposed in the literature and is pretty accurate for XPs that are concentrated in a single metropolitan area. And we also have done some analysis of using reseller remote peering. So networks connecting to a IXP using a reseller remote peering share port. But in this talk, I'll focus on the results we've obtained for the geographical remote peering. We have more details about the reseller remote peering findings on our paper, and you can find that more on that. So some of the questions we want to better understand are how widely deployed is remote peering currently, and how does it reflect on routing data? So we found out that it is widely used, at least in the ISPs we analyzed, and we have seen that it kind of varies on the ISPs itself. So for example, we saw that one of the Brazilian ISPs showed the max percentage of interfaces using remote peering that was around 35%. And for other XPs, it was less than 13%. In terms of how these interfaces reflects on the announced routes and prefixes, we saw that remote peering announced proportionally fewer routes and prefixes than local ones. And the highest difference was also in Brazilian XPs, that around 13% of the interfaces that use remote peering only announce 3% of all the routes in the XP. And one other interesting factor that we found is that for 4 XPs, more than 71% of the prefixes announced with remote peering also had a local peer route. So this high percentage is very interesting because it adds a lot of complexity to traffic engineering and to possibly decide which route, remote or a local one, has the best performance latency-wise. So focus more on this scenario, firstly about the practices with multiple route alternatives at the XPs. So we would like to understand better, for example, considering these multiple alternatives, which routes would be preferred, or if there is a difference in size of them, and if there's a latency penalty of using the remote peering instead of the local one. So in summary, the remote routes, despite being shorter than before, they tend to have a higher latency when compared to the local one. So to that, you can see in the left figure, so it's the routes according to their AS path length. And we can see that the remote ones are majority shorter. The majority of remote routes are shorter than the local ones, and then could lead them to be chosen over the other ones. And when looking at the route views data from BGP, we saw that most of the peers sharing their views of the network were indeed choosing the remote ones instead of the local ones. And in terms of latency-wise, we perform measurements to all of these prefixes we have seen using either the local or the remote one. And we can see that this table with the number of routes that has lower RTT using the remote ones or the local peerings. And we can see that big part of these routes are faster using the local peering instead of the remote ones. And even further, in some cases, for more than 44% of the prefixes, this latency difference was higher than 5 milliseconds. So it shows that it can become considerable difference, and that proper traffic engineering in these cases can be relevant to decide if wanted a route to steer the traffic and lead to better latencies and end-to-end latencies. Yeah. Next, we also to understand, for example, if a prefix only had a remote peering option at 1 XPs, and if it was better to rely on that remote peering connection to send traffic, or if it was better to use a transit provider otherwise. And in summary, the prefixes with only remote peerings, remote routes at the XPs were faster and had lower ITT, but not by a considerable amount. So we done trace routes also to all these routes using the remote ones or a transit provider. And you can see in the table that by the numbers that most remote peering routes had lower latency than a transit provider, so around more than 50% of them. But the latest difference was below 5 milliseconds for the great majority of them for 6 XPs. But we also had some interesting results that in some cases, remote peering can be a substantial advantage in terms of latency. So we have these results for NAPA Africa, and we saw that for more than 80% of the prefixes that had lower RTT via remote peering instead of a transit, the difference was at least 40 milliseconds higher. the latency was at least 40 milliseconds lower via remote peering than using the transit provider. And talking with some of the operators, they mentioned that the high IP transit prices in the region, along with poor ISP interconnectivity, can make the remote peering a more reliable and with lower latency option when compared to only relying on a transit provider. So we highlight that in some cases, remote peerings can be a beneficial option for end-to-end latency. And just then finishing my talk, just to highlight and summarize some of the findings we had in our work. So Infer remote peering is still very challenging, and the state-of-the-art methods have limitations and cannot be accurately used all around the world. We have seen that despite shorter and preferred, some of the remote routes had higher latency for a considerable percentage of the prefixes. And for those cases that you only have an option of remote peering at XP, it was better latency-wise in the transit, but not a considerable amount. So considering this is an ongoing work, I would also like to talk a little bit about the things we're really looking forward to next. So the first one would be we would really like to expand our analysis and measurements to more XPs and to have a more extended set of XPs, especially in relevant areas we have not investigated yet, like the APNIC region. So we know that there's more than 140 XPs in the region with some really big ones. And having a collaboration with some of them would be really interesting and would really improve our work. So we're also looking for ASs that use remote peering to establish some partnership and to investigate how the remote peering is impacting their networks in terms of performance, quality of service, routing efficiency, and how it's affecting their customers' networks as well. And lastly, considering the emergency scenario of IPv6, we would also want to understand if our findings to remote peering IPv4 are also being reflected on IPv6. So yeah, that was my talk, and thank you for the attention and the opportunity to present the work here at APNIC. So if you're interested in contributing or have any question, please feel free to get in contact with me. And if you want further details about research, we have the fun paper. You can also have a look. Thank you.
Thank you very much, Fabricio. Any questions for Fabricio? We have time for 2 questions.
Hello, this is Alex from F5. I have one question about remote peering. An example is in Singapore, there is a lot of people from outside the region. For example, Australian ISPs is coming to Singapore to get routes. They're putting a route in Singapore, but the traffic is still in Australia. Is it remote peering for you?
In our work, we're considering remote peering like if you're not physically present at the XP. Like one case that it could be happening is this like trombone paths, like causing by remote peering, but I don't know if that would be considering remote peering.
Okay, thank you.
Thank you.
One question from online. Thanks. Can we peer IXPs with virtual LANs?
Can we what? Sorry, let me see the question. Can we peer IXP? I don't think I understood the question, but
yeah, the questions can
be
well.
Yeah. Yeah, I think the question maybe is like you are connected to via a layer 2 connection to the XP if you are remote peering, and you are considered a full member of the XP. So you are technically you are in the XP, but you're not. So you are a full member. You have access to route servers. You can peer with everyone else. So that maybe can be considered a virtual LAN in his question. I don't know. Sorry, I couldn't understand the question very well.
All good. Any other questions from the room? No. Excellent. Thank you very much, Fabricio. Everyone give him a round of applause. Thank you, everybody. This concludes technical session 3. Enjoy the rest of the conference, and I'm sure we'll see you around. There is a BOF in this room next. So if you're here for the BOF, stick around.